Thank you for joining us. This video will go over both the concrete tilt-up wall and slender masonry wall modules in the Structural Engineering Library. This will be a general introduction and talk about areas that are used in both of the modules, since both programs are very similar. So with our project file open, we will add a concrete tilt-up wall calculation. And reviewing the tabs across the top, we have the General tab, where you can specify wall materials, wall sizes, and general analysis settings. A Dimensions tab, where you set whether it's a 1 or 2 story walls, some fixity conditions, and some reveal information. A Loads tab that allows you to enter both vertical and lateral loads in the wall. And then, of course, a Loads combination tab. Reviewing, we have a summary of all the results, a review of maximum combinations, strength design results, deflection results, reactions, and some notes about the use of the program. So let's start up here with the General tab. You'll notice we can simply select between masonry or concrete walls, and it shifts all the display of the associated variables. In both sections, we have a materials property section where you can enter in F prime CF sub y. You can enter in modulus of rupture and some other values. Reinforcing, it's a little different between each program. In the tilt-up wall program, we can have bars at the center or each face and any incremental spacing. And the analysis settings, we always use a p-delta deflection method, meaning that the results are iterated for both strength design results and deflection results. The wall is divided up into 30 increments or 30 small segments, and for each segment we calculate the properties of that segment, both gross section properties, crack section property, and also the crack section, the effective moment of inertia based upon the moment level in that particular segment. We do not use the inaccurate ACI equation for calculating the effective moment of inertia of those sections. It's been proven that that ACI formula is not correct. We use Bischoff's equations, which are well published. If you'd like to get some information on those equations, just send an email to support@enercalc.com. Those are under review by ACI and will probably be incorporated. And the most important reason for using those equations is that they yield results that match the test results of slender walls that was done in the early 1980s by the Structural Engineers Association of California. If any of you have designed concrete slender walls or masonry slender walls for a number of years, you know that all the attempts by the UBC and ACI and IBC to give you equations and iterations do not give values that match the actual true test values. So we're going to say that these the analysis method in this program exceeds code requirements because it's so accurate. You can specify your vertical steel minimum percentage in here. That's a display only usage, and we have the standard code required minimum allowable out of plane deflection ratio, which specifies the maximum out of plane deflection. Going over to dimensioning, this screen is identical for both concrete and masonry. We can have 1 or 2 story walls. For the 1 story wall, we enter a clear height and a parapet height, and you can have 3 different types of fixity. Top and bottom of the wall is pinned, top and bottom of the wall is fixed, bottom of the wall fixed meaning a dock high wall, and then top free and bottom fixed for a cantilever yard type wall, which really doesn't need to use this equation for P delta effect design on the wall that we offer. We allow you to enter an initial lateral displacement at the roof that is taken into account to calculate additional moments due to roof loads. We have a reveal capability. This is in concrete wall only, so we'll leave that to the concrete wall section. And then we can enter in our wall width portion. Now, this module calculates all the results for an effective strip width, meaning typical strip in a flat wall, you can just do it 12 inches wide. If you have a wall with a hole in it and you want to design the jambs and they're 3 feet wide, you can put in the strip width of 36 inches to encompass the entire jam width, and then your loading and reinforcing will go from there. For 2-story walls, you'll notice the diagram changes just a bit. You can specify bars in the upper, lower, and level. We have some additional height specifications here, and you can also specify an initial lateral displacement for the second floor attachment. Going over to the loading section, vertical loads, I have let me go back and just change it back to 1 story. It'll clarify this a bit. We have vertical uniform loads. We have 2 of those. A ledger load, where you apply a load in kips per foot at a certain eccentricity off the center line of the wall. And then we have a concentric load, which acts down the center line of the wall and does not have any ability to create any moment. And we can also put vertical concentrated loads on the wall. This is an eccentricity of that vertical concentrated load from the center line of the wall. And then we have, of course, our different types of loads we can add. Here, this is probably better explained in the user's guide, where we can give you some sketches. Distance from base of wall, of course, is simply the distance above the base of the wall where that vertical load is applied. The reason we give you this entry and these 2 entries over here that I will describe is because, number 1, the program analyzes the wall in segments of the vertical height of the wall, and so the actual axial load in each segment is calculated based upon the weight of the wall above it and the weight of loads applied above it. So if we were just to apply this vertical load 3 feet above the base of the wall, why then from 3 feet to the top of the wall there would be no effect of that additional load. Bearing width and base width, that describes how the load is spread out along the in-plane length of the wall. Most people assume that a point load is spread out with an application angle of 45 degrees on each side of the bearing width. That may or may not be true. You may be trying to have a 36-inch width strip with a load applied 12 inches from one edge. So you'd want to do some more definition here. This model has a bearing width of 6 inches standard and a 1 foot base width. That basically means that your concentrated load is going to be confined to your strip width of 12 inches. However, if you had just a big flat wall, let's say 20 feet long with a concentrated load straight in the middle of it, you knew that load was going to spread out at 45-degree angles, why then you might just put the full base width of the wall down here. And then as your strip got closer and closer to the base of the wall, the contribution of this concentrated load would get smaller and smaller as the load spread out wider and wider. Just another item we've added in here to make sure this program gives you a lot of very detailed calculation capability. For lateral loads, we have several different types. Well, we have 2 different types. We have a wind load that you can apply to the wall, and then of course a seismic load. We give you 3 ways to specify that seismic load, just by entering a per square foot value that the seismic will generate. We allow you to enter a wall weight factor. That 0.25 that you see there will just be applied to the wall weight, and that generates the final lateral force, seismic force. Or you can enter SDS, I times SDS per the building code here, and it'll be transformed through the equations to generate a lateral load there. This section here allows you to apply additional lateral loads to the strip width. A concentrated load, that's simple. It's just a concentrated lateral load at a certain height above the base of the wall. we give you the opportunity to enter 2 concentrated loads on that strip, concentrated lateral loads. And then for distributed lateral loads, that of course has a starting point and an ending point measured vertically upward from the base of the wall. And we give you 2 of those loads as well. One of the most common uses of the distributed lateral load section or lateral point load is when you're designing a jam strip and you have to account for the seismic weight of the concrete over an adjacent opening. Typically that load, you will always take that load and apply it to the adjacent jam strip, and you can either apply that lateral load as either a partial length lateral load on the jam at a distance starting at the top of your opening up to the top of the wall, or you could assume that that weight of wall panel above the opening spans vertically between the roof ledger and perhaps a bond beam that you've constructed in the thickness of the wall panel, and then that bond beam would carry the load out to the jam and where it would apply it as a concentrated load. Of course, these are rigid, stiff panels, and the load paths are theoretical anyway, unless you want to do a finite element analysis. So, but these are the most common ways that engineers do the approximations of those loads. Moving over to load combinations, if you've watched any other of the videos or used the software, you know this is the standard load combination screen. You can reload load combinations from the built-in database that you've defined, and you have some abilities to reverse wind loads and seismic loads. That goes through the input. Output is essentially identical for both masonry and concrete. On the summary tab, we have a summary of all the results with a green check mark, or a red X if it doesn't work. We're giving you maximum bending and stretch ratios, which are typically the critical values. Typically, shear will never govern. We give you moment capacity checks, deflection checks, axial load checks, reactions, etc. The rest of the tabs are tabular in nature. This is the factored load maximum moments for all the load combinations. So here it's saying for this particular load combination, the maximum axial load is 1.44 kips. The maximum moment value is such, and area steel and such. So it's just a summary for each load combination what the maximum axial load moment values are. And same here down here for service load maximum deflections. For each service load combination, it's combining the axial load moment. It's telling you what moment of inertia it's used for that segment of that particular design, and we're giving you the deflections and deflection ratios. Going over to strength design results, these are detailed results purely for the bending stress generated by each factored load combination. We give you this is divided up into the distance above the base of the wall in increments, so you can see the increments that the 30 wall elements has generated. So for each of those increments above the wall, we give you an axial load, a moment, some steel area values, and some moment of inertia values that are used for the deflections. Service load deflections, again, for each of the 30 increments above the base, we give you the axial load at that increment, the cracking moment, the actual moment, I gross, I effective. What we really need to do, these I effective values will actually vary. I neglected to put in a lateral load. Put in a high lateral load there. That's a wind load. We'll choose a wind load combination. Oh, that's probably way too high. No. Here we go. Nope. Sorry, I should have been prepared to enter in the correct values to show you how the effective moment of inertia varied throughout the height of the wall. Going over to reactions, here's all of our service load cases and our 2 horizontal reactions and our vertical reaction for the strip width. We have a simple sketch of the wall. I believe this is vastly improved since this video was made. And then we have a simple stress diagram and deflection diagram, moment and deflection diagram for the wall, which I believe also has been improved since this video was made. So thank you. That gives you an overview of the tilt-up program and the Masonry Slender Wall program, and we'll have 2 more videos to go into to give you some details of the specific uses for each material. Thanks for listening.